This video picks up where the previous introduction left off, repeating two of the steps that we've already discussed. Fundamentally, we start with the idea that t hat will be approximated by the sum over j from j equals 1 to the number of nodes of tj nj. I chose to start this video there because it feeds in and takes those terms and incorporates them into the temporal term as well as the spatial terms. You're very familiar with what it looks like in the spatial terms, but I thought it was important to see it in the temporal term as well. This video concludes with the full discrete formulation for the unsteady problem. The next video will pick up with the implementation. I apologize in advance for any of the cat noises and for the rough quality of the video. Another point that I'd like to make, I particularly liked the content within this video because there are a number of points I make along the way that I thought were quite valuable. However, when we start talking about the discretization and the finite difference type discretization of the time stepping, it's sort of glossed over. We don't have a lot of time in the 7-week 2-credit course to discuss finite difference discretizations. If you've seen it before, it will make complete sense to you. If you haven't seen it before, please drop me an email and I'll find some auxiliary material to post onto our site. Step 4 is to approximate t hat by assuming that it's a function tj nj. And we've spoken before about our choice of functions. We choose nj to be a polynomial because it's easy to integrate and it's easy for implementation and computation. Step 5. We're going to say that the w sub I is equal to n sub j. So this is the Gelirken approximation that gives the Gelirken weighted residual its name. So now let's combine the step 4, step 5, and the weighted residual, and we will get then for our full expression, we're going to get 0 to L, the sum over I, sum over j, of Wi nj dx times t dot j, where by t dot here we mean the traditional with respect to time, plus alpha times the integral of 0 to L, sum over I, sum over j, dw dwi dx, dnj dx, dx times t of j minus alpha wi dt hat dx evaluated at 0 and L. And I have a couple of comments to make. One, notice that this is still dt hat dx because the boundary condition will be given as a function of dt hat dx. So this is this will be, this is the type 2. Type 2 boundary condition. There will be a separate video about the type 2 boundary condition, but you can basically see how you include it in the approximation and in the formulation. Another point to call out is that this term right here can be written in many ways. It could be written as 0 to L, Wi nj dx times t dot j. It can be written as 0 to L ni nj dx times tj. Or it could also be written the one other way. So I'm going to say this is A, B, one other form that you're going to find. And I write these because this is what you'll find in the literature and in other books. Phi, Bj, dx, tj. These are all equivalent. Where you see the Wi nj, you're assuming summation. This is indicial notation. Some books will use n. They'll say, look, we've already said that Wi is going to equal nj, so we'll just use ni and nj all the way through. They're the same function. Some places, rather, particularly in the math text, you'll find phi, pj as the notation. I will stick with the Wi nj so that we can denote that we've got a weight function and a basis function. As you go through, if you wish to use NINJ, Phi, Pj, that's fine. For ease of keeping the pieces clear while we learn it, I think WINJ is the way to do that. So consider the temporal term. So we know from calculus that dt is equal to, in the limit, as delta t goes to 0, delta temperature over delta time, which we can express as Tn plus 1 minus T of n over delta t, where delta t is your time step. So, and we're going to say that T of n plus 1 is equal to T of n plus delta t. So, furthermore, this assumes that T of n is known everywhere. So T of x, Tn is equal to known. So our goal is to determine T of n plus 1 j. And how are we going to do that? Basically, we're going to look at, for the temperature, for the time term, we're going to evaluate it. We can evaluate it at n plus 1, and we'll set a given delta t. But where do we evaluate the spatial terms? And by where, so really this means which time which time slice. So if you think about this, you can think about, let's set, here are some nodes. And if I have these are different time slices. So the nodes are actually, here we are at the spatial, each, as I go across, these are each spatial values. But I've got time t equals 0, t equals delta t, t equals 2 delta t, dot, dot, dot. So this is a finite difference method. So what I'm looking at is I'm looking at a stencil. So I'm taking, if I think about just projecting forward, I can take this value and project it there, this value and project it, and that value and project it. And I can find an average of those three. I can do the same here. I can do the same here. Then for the next value up here, I can go up here. And here I can go across. But what you find is that by the time that I'm back up here, using this, this, and this, if this is my boundary, I'm losing track of some of my values. They're not feeding in. They're sort of feeding in slowly. So the question is, do I just move forward? Do I solve implicitly at each time step, an implicit problem, or do I do some mixture? So what we want to look at is what is referred to as the theta method. And in this case, theta is equal to a relaxation parameter. And theta is between 0 and 1, and we'll see how that all fits in just a minute. Using our theta method, we're going to say that t is equal to theta of Tn plus 1 plus 1 minus theta Tn. If theta is equal to 1, that will give us a backwards implicit scheme. And so basically what happens when theta is equal to 1? It's all based on Tn plus 1. When theta is equal to 0, that will give us an Euler forward scheme, which is explicit. We can just look and see if theta is equal to 0, then what we have is it's entirely based on the previous time step. There's an additional method with theta equal to 1/2 that will give us the Crank-Nicolson, which is a second order finite difference. So these are the values. These are the stable values. They lead to accuracy and stability, which we won't discuss much in this course. This is one of the places where we have to take into account the stability. What I had said in class the other day was, consider a parachute. You suddenly fling it up in the air, you jerk it up. You watch the undulation of the wave within the parachute until it settles back down to just a steady quiescent state. If you have a method that's not stable, then that will shoot up and it may never settle back down because of numerical instability. So what does this mean for our solution? What happens if we now say that t is equal to theta times Tn plus 1 plus 1 minus theta T of n. So let's substitute that in to our weighted residual formulation. And what we're going to have is 0 to L Wi nj dx, where I've taken the summation out and we have implicit summation, Tn plus 1 minus Tn over delta t plus alpha times 0 to L of dwi dx dnj dx times theta tjn plus 1 plus 1 minus theta tjn. These should have j's. Minus wi of alpha beta dt n plus 1 dx plus 1 minus theta dt n dx, evaluated at 0 to L is equal to 0. So what I'd like to do is I would like to rearrange this so that what I'm going to do is I'm going to have my left-hand side will be 0 to L Wi nj dx plus alpha delta t theta 0 to L dwi dx dnj dx dx times tj n plus 1 minus theta delta t wi alpha dt n plus 1 dx 0 to L. There's our left-hand side. Our right-hand side is 0 to L Wi nj dx plus alpha delta t theta minus 1 times 0 to L dwi dx dnj dx dx, all of this times tj of n minus theta minus 1 delta t w of I alpha dtn dx between 0 and L. So that this is now the entire formulation. Notice that everything on the right-hand side is known. But now it's clear what that right-hand side term was, why there was a right-hand side term in the previous code. So the rest is about the implementation. We now have the finite element model. We will go ahead and we will work on the implementation in a separate video.